we have a sort of flattening of the curve now.
Right.
The number of cases started decreasing, but still, the whole India, we have around 4,000 deaths every day.
Mm,
4,000 people died because we are 1.25 billion people. In Kerala, we have 33 billion people, and we have around 150 deaths every day.
yeah, it's a
Yeah.
pity part is that one.
Yes. How about Malaysia? Also understand that you are
Well,
50.
keep on increasing.
Yeah, it's
Uh,
very yeah.
so, Prof, I think I'm going to start shortly.
Start, start,
Okay, all right.
start.
So, Assalamualaikum and hello everyone. Welcome to today's session organized by AMSERU. So, I am Dr. Shazwani Muhammad Zaki from the Departments of Manufacturing and Materials Engineering. So, for your information, AMSERU stands for Advanced Materials and Surface Engineering Research Unit from Department of Manufacturing and Material IIUM-KL. So if you can see my background, you can see our beautiful campus located in Gombak, Kuala Lumpur. Okay, so it is such a great pleasure to have Prof. Sabu Thomas as a speaker for our webinar today. So without further ado, I would like to invite our advisor, AMSERU advisor, Professor Malik, to give a welcoming speech. So please welcome, Prof.
Not as an advisor, but on behalf of our
Hi.
HOD,
Okay.
head of the department. Anyways, Assalamualaikum warahmatullahi taala barakatuh, and very good morning.
Waalaikumsalam warahmatullahi
Salam.
wabarakatuh.
Morning, Prof.
Morning,
Morning,
Prof.
Prof.
And everyone.
Okay, very good. Then I don't need to talk loudly. The reason why I loudly paid salam so that everybody wake up. And being the opener of this webinar, I don't have to talk. I'm not the presenter. I'm not the speaker. Speaker is there. So rather to open up and wake up everybody. So hello everyone. So and again, welcome to today's AMSERU webinar session on the topic of new opportunities in sustainable nanomaterials. So our guest speaker, as mentioned, is Prof. Dr. Sabu Thomas, is the Vice Chancellor of Mahatma Gandhi University in India. And our moderator for this webinar session will be our Assistant Professor, Dr. Shazwani Muhammad Zaki, from our AMSERU unit and also Department of Manufacturing and Materials Engineering, Faculty of Engineering, IIUM. So dear participants, brothers, sisters, I'm not going to take any time from you, as I told, I'm not the speaker, but to wake up everybody. So, and this is a part of our series program or monthly program. Now we call online monthly webinar. Before we used to say that monthly seminar when it was F2F. So now no F2F. So that's what we call online monthly seminar, webinar. So our main aim is to provide the key information and knowledge in the field of advanced materials, especially for today on nanomaterials or otherwise nanotechnology. So in this virtual platform, I also welcome our guest speaker from India for sparing his valuable time with us and share his vast knowledge in the field of nanomaterials and nanotechnology, followed by a question and answer session. Dear brothers and sisters, we all understand the importance of nanomaterials and its nanotechnology, or its technology behind, in our day-to-day life and the ways in which they are transforming the world. Ladies and gentlemen, I am especially pleased that this webinar will go along with discussion, question and answer session, and I believe also can go up to the sort of discussion on the collaboration part, finding the opportunity for collaboration, as it is equally important for us to enhance our research activities and research profile. I am confident that you will find new ideas, new technology, new sustainable materials, and also, as I mentioned, is the way to collaborate with others, especially with the Mahan India, in presence of this our guest speaker. We would love to hear from you if you have any question, comments, and any sort of suggestion. I wish you all a very successful webinar. Thank you. Thank you very much to everybody. That's all.
Thank you, Professor Malik, for great welcoming speech. Okay, so I would like, for housekeeping purposes, I would like to remind to the audience to turn off your mic so that we can avoid any distraction. And then for your information, will be running a live Q&A session at the end of the webinar. So if let's say you have any question to ask Prof, you can just popping the question in the chat box, and we are going to have like interactive session after Prof finish with his talk. Okay, so I'm going to introduce our speaker background, just a brief introduction, because when I look on Prof Thomas' website, if let's say I have to read everything, maybe I need a couple of hours, Prof, to read your background, your achievement. So I believe some of us, we are familiar with Prof. Sabu Thomas. He is a Vice Chancellor in Mahatma Gandhi University, Kottayam, Kerala, India. So he is a professor of polymer science and engineering in School of Chemical Sciences, and also a founder director of International and Inter-University Center for Nanoscience and Nanotechnology. So his academic career started in 1984 as a senior research fellow, and Prof. Sabu obtained his PhD in 1987. So Prof, I was born in 1986. Okay, his research focuses on polymer blends and polymer composite. Prof. Sabu has received numerous prestigious awards and prizes in research, and also Prof has established various collaboration and secured industry supported projects from USA, and also Czech Republic. Okay, for your information, 76 PhD students had completed their PhD studies under Prof. Sabu's supervision, and at present, he is supervising about 15 PhD students and 9 postdoctoral researchers. Prof also has published many papers in prestigious journals such as ACS Sustainable Chemistry and Engineering, the Journal of Applied Polymer Science, and many other journals. And his impactful research is proven with his hash index score over 100, which is really amazing, Prof. So I think without further ado, I would like to invite Prof. Sabu Thomas to deliver his talk. So please welcome, Prof.
Very good morning to all of you. I'm very excited to be with you today. And thank you, Professor Saki, for the kind words of introduction. And many, many thanks for the introductory remark of Professor Malik and all my academic friends, students. I'm really delighted to be with the International Islamic University today. And let us share our knowledge. Let us make a very active cooperation between our group. My university is located in Kerala, very south of India. So most welcome to our university. This is a quite big university. We have every year we have 400,000 students enrolled at the university. We have 267 colleges under our university. So it's a huge enterprise. So I am open for all sorts of collaborations, cooperations, student exchange, faculty exchange. So after the pandemic, you are most welcome to visit us. I'm going to talk today on a very important topic, which is already announced, new opportunities in sustainable nanomaterials. And I'm right now the Vice Chancellor of the university. For the last 2 years, I have 2 more years to go. And I have a very active group in chemistry and nanoscience. Those who are really interested to look at my activities, you can see my website, sabuthomas.com, iiucnmgu.ac.in. So what I'm going to talk today is how we can make use of our agricultural waste as a wonderful material for advanced functional applications. Specifically, I will talk about plant waste. I will talk about waste from the fish industry. These two waste are very, very important, and we can make beautiful, sustainable nanomaterials. That is the essence of my talk. This is the emblem of the university. And you can see a spindle wheel where Mahatma Gandhi taught us the principles of self-reliance. He said during independence time, he said everyone should make their own clothing material and you should not use the British-made clothes. This is a part of our independence struggle and to teach the people of India the principles of self-reliance. And you can see the emblem of my university. My university was started in 1983, commemorating the father of our nation, Mahatma Gandhi. Let me show you my first slide. Can you all see this slide? The slides are moving. Are you able to see my next slide? The slides are moving?
No, Prof. I cannot see any slide, I think.
Oh, you cannot see any slide. Okay.
Yeah.
What I will do is...
So go present now.
Yes. Can you...
Top right corner, present now. Click present now icon.
Yeah.
And then click a window.
Yes, yes.
On the screen, can you see your PowerPoint slide? If that, you have to select that.
Yeah,
and then click share.
Yes, I am trying to do that.
Probably delay, slight delay.
Coming
I
up,
can
coming
see
up.
now. Yeah, it's coming out. Yes, Prof.
Can you see my slide?
Not
Yet.
not yet. Maybe still loading. But I can see at the bottom, Sabu Thomas is presenting, but I cannot see the slide.
Oh,
Yeah.
okay. I will try again. So now I will take the window. That is better.
Yes, a window, yeah.
Yeah. Is it okay now? Can you all see my slide?
Yeah, coming up. Yes, came already. Yeah, it's a nano size. Good. If you want to make it macro size, also can. Slide nano size.
Is it okay now?
No, Prof. Cannot see your slide.
No, I can see. I can see.
Oh, I cannot see.
Slide is visible now.
Okay, yeah. Maybe
Are you able to see my slide?
Yes.
Oh, yes, Prof. Okay.
Now I'm going to check one more thing.
Yes.
Can you see my next slide?
Yes.
Better go know the menu.
Are you see
And then
my
select the slide show.
Yeah, I'm showing the slideshow. Can you see my next slide? Is the slides moving?
Not yet.
Not yet.
You're still seeing the first slide.
Yes.
Yeah, but it is not in slideshow mode.
Yeah, because are you able to see now? Is the slides moving now?
Yeah.
No.
Yes, it's moving to the second slide. Yes.
Yeah, you see, there is some problem sometime. So I will probably talk in this mode. This is better because otherwise, if I go to the other mode, the slide will not move. There are some trouble sometimes. So see, now you can all see my first slide, right? New opportunities in sustainable nanomaterials. Can you see?
Yes,
Yes,
very
Prof.
clear, clearly.
We
crystal
will
clear.
go in this mode. And those who want to know about my work, please go to the website sabuthomas.com, where you can see all my books, all my research publications, all my patents. You can see my collaborators worldwide. You get a lot of information from this website. Our facilities, we have state-of-the-art facility at the campus. We have electron microscope, we have magnetometer, we have airfoam, we have X-ray, we have state-of-the-art technique. So today I'm going to talk about how we can make use of the waste, agro-waste, into sustainable nanostructured materials. Can you see my next slide?
Yes, Prof.
Yes, very good. See, I'm going to show you the ACS statistics. American Chemical Society gave a very good information. This ACS says that 1.6 billion tons of agro waste is being accumulated every year around the globe. This is something very huge amount. And very important point is these agro waste are not effectively utilized. And many farmers, they burn the agro waste, polluting our ecosystem. So there is every need to utilize this agro waste into advanced structural materials. It could be waste from agricultural land, it could be waste from the fish. I know Malaysia, you all like fish, right? And I had wonderful fish when I visited Malaysia. Let me now show you another important slide. What are the different agro waste? Sugarcane bagasse. I'm sure you have a lot of sugarcane bagasse in Malaysia. Wood flour, wheat bran, rice bran, jute, coir, pineapple, hemp, bamboo, oil palm. Now Malaysia, we have a lot of oil palm. When I land at the airport, I see beautiful oil palm field. Fish industry waste, waste starch from agricultural field. It could be potato, it could be cassava, it could be grain, it could be rice. So all this waste have to be converted into advanced nanomaterials. Let me show you a very important table. This table indicates that the most important agricultural waste is the wood flour. You see the production of wood flour, number one, followed by bamboo. They are obtained from the stem of the plant. Coconut. Kerala has a lot of coconut trees. We have a big industry on coconut, jute, canaf, flax, sisal, oil palm, variety of fiber. Let me now tell you the salient features of these plant fibers. Environmentally friendly materials. They're non-toxic. They're cost-effective. They're lightweight. The world is now moving towards lighter and thinner materials. They are non-abrasive to machineries. If you use glass fiber, your machinery gets abraded very fast. High specific properties. If you look at this property divided by density, they can beat with glass. Underutilized, sustainable. So these are societal need. And those who are really interested, you can read my fantastic review on carbohydrate polymers. Now, plant fibers are classified based on their origin. Must from the stem. Good example is jute. Leaf from the leaf of the plant. Good example is pineapple. Seed. Good example is coir. Grass. Good example is bamboo fiber, elephant grass. You see some of the nice pictures. You can see oil palm that you have a lot in Malaysia, and you have lots of activities related to oil palm. Banana, we have plenty in Kerala. We have plantations of banana in Kerala. Pineapple, we have very big industry of pineapple in Kerala, but the leaves are not being utilized. Now I'm establishing a plant in the campus to extract the fiber from the pineapple leaf and fiber from the banana plant. Coconut is a big industry in Kerala. Let me now show you the price of this material. Taking cotton as an index for 100, you will find that all these fibers are relatively cheaper. Look at wood flour, look at straw, look at coir. They're much cheaper than glass fibers. Let me now show you the mechanics of this material. I'm sure you are all engineers. If you look at the strength, tensile strength, if you look at the Young's modulus, if you look at the elongational break, plant fibers give excellent values. Additionally, I request everyone to look at the density. Density is much lower than glass, therefore, the specific properties are even better than glass fibers. Property divided by density. That's extremely important. Let me now tell you the constitution of these plant fibers. Lignocellulosic, the main component is cellulose. And you can see the beautiful structure of cellulose. You have fantastic hydroxyl groups, amenable to chemical reactions. So this is a wonderful molecule for a chemist. A chemist can do a large number of reactions on the surface to make it hydrophobic, to make it hydrophilic, to have electrostatic interactions with other matrices. Look at the structure of lignin, a complex hydrocarbon polymer. Now we have strategy to make nanolignin. Look at hemicellulose. So this is a wonderful material. Now let me show you the hierarchical structure of plant fibers. You can work in different length scales. Macro length scale. I remember in '87 when I started the university after my PhD from the Indian Institute of Technology. I have lots of industrial cooperation on macrofibers. Chop the fibers, put into plastics and make composite. Then we focused on microfibers. See, inside the macro, we have hundreds and hundreds of microfibers. Inside the microfiber, you have nanofibers. Now, today I'm going to talk about these nanofibers. So this is the beauty of plant cell. You have a hierarchical structure. Now I'm going to give you another important slide. Why nanocellulose has become so important? I would say this is the most important nanomaterial for mankind, a strategic platform for sustainable development. Highly crystalline, excellent mechanical strength, low density, high water holding capacity, high aspect ratio. You can mix with several polymers and you can make fantastic advanced structural materials. If you look at plant fibers under electron microscope, you see a beautiful web of structure. Look at this. This is plant fibers under electron microscope. The diameter is a range of 20-25 nanometer. And if you look at nanofibers, it's enormously long. It could be, the length could be in the range of micrometers, several micrometers. If you put this nanocellulose and made a gel and put in a transparent glass, polyethylene glass, you see, look, this is a beautiful gel of nanocellulose. How do you make them? You make them by high pressure homogenization. You make them by grinding process. You make them by cryocrushing. You can make them by acid hydrolysis. You can make them by steam explosion process. You can make them by high density ultrasonication process. So these techniques have been matured now. Let me quickly go through it. High pressure homogenization, you all must read the paper of Professor Frohn. High pressure homogenization process includes passing the cellulose slurry at high pressure into a vessel through a very small nozzle. And this high velocity and pressure put a lot of shear force on the fiber and you get nanoscale material. This is the story of high pressure homogenization. Look at super grinding introduced by the Japanese Professor Abe and Iwamoto. It's a beautiful paper in biomacromolecules. Now the technology is mature now. There also you apply high mechanical force using grinders. and you can get beautiful nanomaterial. This is the FESEM of the the nanomaterial. Beautiful material you can make. Look at cryo crushing. Cryo crushing is also again a very wonderful material process. You decrease the temperature, you freeze it, and then you crush it. High intensity ultrasonication process. This is again a mechanical process in which oscillating power is used to isolate cellulose fibers by aerodynamic forces of ultrasound. You must read the paper of Professor Wang. Look at steam explosion process. We have quite efficient steam explosion units. Steam explosion is a wonderful technique. You put everything into a chamber, an autoclave, a pressure of 137 Pascal, temperature of 150 degrees Celsius. You run the machine for a few minutes with the nanocellulose, with the plant waste inside. Then you suddenly release the pressure. Then you have an explosion. That is why we call it a steam explosion. And the cellulose fiber is opened up. You remove reluctant heavy cellulose by chemical hydrolysis, and you get the nanocellulose. Let me show you the totality of the process in my laboratory. My PhD students go to the plantation and collect the agricultural waste. And then we go for nanofield treatments and bleaching. You get latent hemicellulose. Then you make a slurry. You get a slurry. You go for a mild acid hydrolysis or a strong acid hydrolysis. If you go for a strong acid hydrolysis, you know what you get? You get short nanocrystals. If you do strong acid hydrolysis, you get small nanocrystals. If you make use of light acid, you get long nanofibers. Look at it. Then you go for a homogenization. You get a white emulsion, and then if you examine under electron microscope, what you really see is nanofibers. So manufacturing is quite simple. I told you that if you use strong acid, you get short crystals, nanocrystals. If you use weak acid, light acid, you get long nanofibers. If you use a strong acid, what happens? The strong acid can kill all the amorphous part of nanocellulose, and you get short, pointed nanocrystals. What is the property of this material? See, the strength of the material is 10 gigapascals. Modulus is 130 gigapascals. What's the typical modulus of polymers? The typical modulus of polymers is in the range of 2 or 3 gigapascal. Look at the modulus of nanocellulose. That is why polymer technologists are really interested to put this material into polymers to reinforce polymers. Let me show you the fantastic work of Muhammad. Muhammad did some very interesting work. He made use of plant fibers and then used strong acid hydrolysis. Look at this. He got short nanocrystals. Short nanocrystals. He used 65% of sulfuric acid at 45 degrees Celsius. Let me show you our laboratory setup. Those who are really interested to work with us, you are most welcome to visit our laboratory. You can send your students, postdocs, send your young faculty to work with us. My PhD students collect the agricultural waste material, the fiber. We subject them into a steam explosion process, followed by bleaching, followed by acid hydrolysis. Sometimes we repeat this process till we get nanoscale. And then we go for a centrifugation, crushing, and finally we get beautiful nanofibers. I will show you some of the structures we have made. This is the structure we have made. A PhD student of mine, right now he's a postdoc in US. He made nanocrystals from banana stalk. Collected the banana stalk, did all the processing, and he made beautiful nanofibers. Look at the work we have done with Sweden. We had a long India-Swedish program. My PhD student went to Sweden and he made use of wood flower. Sweden has a lot of wood. So we worked with wood flower and you can see beautiful nanofibers. Beautiful nanofibers we have made from wood flower. Look at our Brazilian collaboration. I had a very strong collaboration with the South Pole. A student of mine, Bibin, went to South Pole University, and we made fantastic nanostructures using pineapple leaf fiber. Fantastic structures we have made. Now I wanted to show you, if you're a chemist, you can do fantastic modification on the surface of nanocellulose. As I showed you earlier, you have beautiful hydroxy groups. You can do Chembo-mediated oxidation process. OH could be transformed into COH. You can do esterification process. You can do polymer grafting. You can do fluorescent labeling. You can do catalyzation reaction. You can do cellulation reaction. You can do lots of reactions on the surface of nanocellulose. You see? So wonderful chemistries could be performed on the surface of nanocellulose. Now we have a cooperation with a chair company. A PhD student of mine is doing cellulation reaction to make nanocellulose natural rubber composite for tire tread. We have a big project with a chair company in India. Now I'm going to show you this material could be utilized for a variety of applications, for EMI shielding, wound healing application, sustain the release of antibiotics, as an wound dressing because it can absorb a lot of moisture, water. Water purification, filters, we can manufacture filters. We can make sensors out of it. Let me now show you our work on water purification. You know, water is increasingly contaminated everywhere, all over the world, in Malaysia, in India, all over the world, water is increasingly contaminated. Pollution from industry, human intervention, pollution from oil. And how can you purify water? I want to show you a beautiful slide. We worked on a membrane which has 3 layers. The bottommost layer, which is polyacrylonitrile. Just above that, we have electrospun PVDF. On the top of this, we have made a coating with nanocellulose dispersion. This is hydrophilic. And if you have such membrane, you can remove dyes, you can remove nanoparticles, you can remove heavy metals, you can remove oil, you can remove bacteria, you can remove viruses. Look at our strategy. This is actually a textile factory, and you can see the textile factory is pumping out millions of liters of water into the river, and this water is increasingly contaminated with a dye called crystal violet dye. It's a very important dye for textile industry. We thought of to catch this dye, how we can purify this dye, to purify this water, removing this dye. And we did a wonderful work. A PhD student of mine, those who are really interested can read our paper in ACS. A PhD student of mine, he made nanocellulose, Dibu Kopakumar. He made nanocellulose, And he made a beautiful chemistry, green chemistry, reacted this with the meltrum acid. Very simple chemistry. And we could introduce CO minus group on the surface of nanocellulose. Once you do that, you know what is the beauty? Once you do that, the modified cellulose, this is a modified cellulose with negative charge, CO minus, can trap the crystal violet dye by electrostatic interaction. Look at this electrostatic interaction between the modified cellulose and the dye. And you see all the dye particles could be retained at the top of the filter by electrostatic interaction. Now I want to show you what is the filtration efficiency. Look at the filtration efficiency. This is the commercial filter, a bi-layer filter, where you can see the removal of crystal violets. Not very efficient. But if you modify the top surface of the filter with nanocellulose dispersion, look at this. The red one is neat nanocellulose. The top of this, the best one, the chemically modified nanocellulose with CO minus group. Look at this. The efficiency became 4 milligram per gram. Unmodified, the efficiency is something like 1.5, 1.25. So we have indicated that by suitable chemistry, nanocellulose could be a good platform as a coating for commercial filters. Now let me show you another important slide. Probably you all know that water is increasingly contaminated with suspended particles, metal oxides. So we focused on iron oxide in the range of 50 to 100 nanometer. So what we did is we gave a coating with the nanocellulose dispersion on the surface of the filter. And when you do that, the whole size becomes around 8.6 to 6.3 nanometer. So all the suspended particles in the range of 50 to 100 nanometer could be reached at the top surface of the dye because they are big. And you might be surprised to see the separation efficiency. Look at this. All these suspended nanoparticles, these are all metal oxides, iron oxide, they're all retained the top surface of the dye, surface of the filter, because they are bigger in size. Look at the bottom part of the filter, electrospun PVDF. No particles. And you also look at the impure water, which is black, because a lot of iron oxide particles. It's completely opaque, no transmission of light. After filtration, you see, you get pure water, 100% transmission. That means we could remove almost all the suspended particles. Now let me show you the work of Korhonen and group from Finland, Scandinavia. They did some very interesting work. You know what they did? Look at this picture. They made aerogel out of nanocellulose. That's a very simple process. You disperse nanocellulose in water and go for a freeze-drying process. And if you can do that, you get beautiful aerogel. And the Finnish group, you know what they did? They did something interesting. They made the surface of this aerogel hydrophobic. How did they do that? They did a coating of TiO2, titanium dioxide coating on the surface of aerogel. 7 nanometer coating on the surface. You know, the plant diameter, the diameter of the nanofiber is 25 to 30 nanometer. So they gave a coating of 7 nanometer on the surface. Once you do such a coating, look at this. Surface become hydrophobic. So this surface can absorb all the oil. The red one is oil. This is seawater. It can take all the oil. It cannot take water because it's hydrophobic. Once the oil is absorbed by this aerogel, you can recycle it. You can squeeze out the oil and reuse it, or you can burn it. You see, you know that seawater is increasingly contaminated because of ships, sinking of the ship is a usual cause for the sea contamination, particularly with oil. And you make nanocellulose aerogel, make it hydrophobic, sprinkle in seawater, collect it, and then you collect it after absorption of oil. This is the way you can remove oil from water. Let me show you another interesting work where you can remove chromium from water. Chromium 6, which is electronegative. And what you have to do is, chromium 6 is electronegative. What you have to do is you modify the nanocellulose with amine group, polyvinylamine. And when you put amine groups on the surface of nanocellulose, become electropositive. And there could be electrostatic interaction between chromium and nanocellulose, and you can remove this. You can see equilibrium absorption process. Similarly, you can remove nickel, cadmium, and lead. You see, probably you all know that in villages, people use rice straw or wheat straw for purifying water. This is a village technology. And there's a comparison with the village technology. Look at this. This is rice straw, removal of nickel. Rice straw can remove nickel, but not as efficient as nano. The red one is nano. And the white one is simple microcellulose filter. You can see, in all the slides, nickel, cadmium, and lead, the nanocellulose having a very good performance. Look at the next slide. Problem with the bacteria and virus. We are all facing the problem of coronavirus. That is why I could not visit your institute. Otherwise, I would have come. I would have flown to Malaysia. It's only 4 hours flying from Cochin to Malaysia. I would have come and spent a couple of days with you. And because of the pandemic, we cannot do it. And I want to show you some interesting slide where nanocellulose can kill bacteria and viruses. If you want to remove viruses are very small, tiny stuff. It can get through all these membranes. If you want to remove viruses, you have to do some chemistry on the surface of nanocellulose. Again, polyvinylamine is the best one. Look at this polyvinylamine. The best way. You put positive charge on the surface of nanocellulose. You all know that viruses have a protein envelope which is negatively charged. And you make a filter. You pass the water through the filter. And all the viruses could be caught by the nanocellulose by electrostatic interaction. And bacteria, it's bigger in size, so it could be separated by size exclusion principle. So you can remove bacteria, you can remove viruses. Let me now show you another important slide where nanocellulose could act as a good scaffolding material. You can see a gentleman suffering from high degree of burns on his face. And you see his face is covered with nanocellulose gel. And nanocellulose gel, if you examine under electron microscope, is extremely porous. Therefore, the tissue generation is too rapid. So this is a wonderful scaffold for burns. Let me now show you one interesting work we have done with Sao Paulo University in Brazil. My counterpart in Sao Paulo University, Alcides, Prof. Alcides, is very active in making polyurethane, medical grade polyurethane. So we decided combining medical grade polyurethane with the nanocellulose. Look at the neat polyurethane modulus, 37.5. If you put 5% of nanocellulose from pineapple leaf fiber, look at this, 992.4. That's the beauty of nanocellulose. And strength also goes up. Finally what we have made, my Brazilian collaborator, working with a Brazilian hospital, he made nanocellulose polyurethane prosthetic heart valve. You can see the valve implant, heart valve viewed in different positions. Nanocellulose is an excellent platform for wound healing application. I'm going to show you how wound healing happens, how it can act as a sustained platform for releasing antibiotic. I wanted to show you the work of Sebastian Moritz from Spain. What Sebastian did is, Sebastian and group made aerogel of nanocellulose. You know, you take nanocellulose and water, you go for freeze drying, you get beautiful aerogel. And then he introduced the antibiotic. Quinine is the antibiotic he used. Look at the sustained release of antibiotic. The antibiotic is released in a very sustained fashion. And he has modeled it. And being a biocompatible material, nanocellulose aerogel is an excellent platform for delivery of, sustained delivery of various drugs. Let me show the work of Professor Liu in China. Professor Liu and colleagues made nanocellulose collagen composites. Collagen is very, very biocompatible natural polymer. And density of the material is 0.02 to 0.03 gram per centimeter cube, very light density. And porosity is 95%. So he combined nanocellulose and collagen and made aerogel. You look at the water absorption capacity of this is 4,000%. And Professor Liu said this is an excellent material for wound dressing. When you use a wound dressing, it should absorb all these pusses and water and all. Professor Liu, very commercialized. Now I want to show you another of Professor Ko. He's very active in making filters. According to Professor Kao, he suggested that many of the membranes that you get from the market, they all have weak mechanics. Look at this polyacrylonitrile membrane, electrospun membrane, very weak. These are all electrospun. But if you give a coating with the nanocellulose, this is one side coating. Look at the strength. The strength goes up. Both side coating, red one. So typical commercial membranes could be made stronger by coating with nanocellulose. Now let me show you something we have done during our, the last 2 years. This is a Indo-US project we proposed, making a new mask. And this new mask we proposed are 3 layers. The outer layer is made of polyester, coated with a polyelectrolyte layer, which can repel, this anti-hydrophilic, hydrophobic layer. It can repel coronavirus. And the middle layer is made of electrospun nylon, coated with positively charged nanocellulose and some curcumin. Curcumin is antiviral. And the innermost layer is made of cotton. It goes to your mouth. And all the coronaviruses coming towards you could be repelled by this outer layer because it's hydrophobic. If at all some coronavirus getting into your mask, this middle layer can kill them because it has positively charged nanocellulose. It can interact with coronavirus, which has a protein envelope which is negatively charged. So it's an electrostatic interaction. Additionally, we also introduce curcumin. And the innermost layer is most comfortable cotton, which is in contact with your mouth. And you can see our design, the outer layer, the middle layer, and the inner layer, which is cotton. These are all mask configuration. We also propose to make it by 3D printing. Now let me show you a few more applications. This is an exciting material for manufacturing sensors. Probably I will show you two examples. First example is a combination of nanocellulose. CNC is cellulose nanocrystal, and CNT, carbon nanotube. You combine both. You want to make a sensor, we need to have a conducting material because it works on the principles of conductivity. So if you look at this manufacturing process, nanocellulose crystals, CND, mix them together, and then you mix with natural rubber latex. Go for a coagulation process. And then you go for pressing, and finally you get a natural rubber composite filled with nanocellulose and CNT. The next slide, you will see what is the purpose of combining nanocellulose and CNT together. You will understand the reason. This is a very simple experiment. In a small glass bottle, you take nanocellulose. Keep it for 24 hours. Very stable, no settling down of nanocellulose crystals. You do the same experiment with CNT. This is CNT in water. And you keep it for 24 hours. What happens? Very unstable. CNT settles down. But you take a 50-50 combination of CND and nanocellulose together. Look at no settling down of CND. You get fantastic dispersion. The same thing you can get in when you mix this combination of two filtration rubber. CND and nanocellulose together in natural rubber. Excellent dispersion. Otherwise, CND cannot be dispersed in rubber because CND forming a bundles. If you use CND alone, you see lots of bundling of CND in natural rubber. Now I'm going to show you the most interesting observation. If you put carbon nanotube into natural rubber, of course you get a percolation. After 6 volume percent of CNT, this is a percolation region. This is conductivity as a function of CND volume fraction. Need natural rubber and CND together. But if you combine CND and nanocellulose together, nanocrystals together, look at the percolation is shifted to lower concentration of CND. You get a percolated structure at 1.5 concentration of CND. And this combination is excellent mechanics, good modulus, good strength, at the same time highly conductive. And this is a beautiful material for sensing. I want to show you another example. Combination of graphene oxide and nanocellulose. The same protocol, you take a nanocellulose crystal, graphene oxide, mixing with the natural rubber latex, you make a composite. And you see, if you use reduced graphene oxide alone in natural rubber, you have a percolation process beyond 1% of RGO loading. But if you combine RGO and nanocellulose, you see the percolation should be shifted to lower concentration of RGO. And mechanics were superior because RGO is dispersed well in rubber. So my dear friend, there is a lot of scope in combining nanocellulose with other nanostructures. You get excellent dispersion. Now let me show you some of our recent work we did. Look at this. This is something we have done with my PhD student, Gopakumar. Gopakumar made nanocellulose from banana stalk. And then he added aniline into it. Polymerized aniline on the surface of nanocellulose. You know what Gopakumar made? Gopakumar made very thin, flexible, conductive nanocellulose paper. I will show you the protocol of this manufacturing process. This has come in ACS. So next slide, you can see this is very interesting. This is the nanocellulose dispersion. He injected aniline, polymerized. He went for a vacuum filtration process, went for hot pressing, and he made flexible paper, which is black. Why? Because you have polymerized aniline. What's the application of this? Extremely conductive. You can see this. And the application of this material is EMI shielding, electromagnetic interference shielding application, particularly for mobile. If you look at the mobile, you have a metallic EMI shielder. And we have shown to Department of Electronics, Government of India, that you can remove all these metals by lightweight, thin, polymeric, nanocellulose shielders. And we got a shielding efficiency of maximum was very close to 24, 23 EMI shielding dB. Let me show you a couple of slides, then I will conclude my presentation. We are also active into, as I mentioned in the beginning, we are also active in fish waste. And Malaysia, I know you are all fish lovers, particularly prawn and crab. My PhD student had a very interesting work. He went to the Kottayam fish market, the city fish market, and collected all this, the shell of prawn and crab. And then he did the processing in my laboratory. This is a structure of chitin. Your NSCO CH3 group. And then he made, by astral hydrolysis, he made nanocrystals of chitin. This is nanocrystal. He also made nanofibers of chitin. If you use a weak acid, you get nanofibers. Let me show you one slide for the applications material. If you look at the nanochitin, nanochitin is extremely hydrophilic because of its hydroxyl groups. But you can make hydrophobic by putting lengthy alkyl group on the surface, reacting with the bromohexadecane, a very simple chemistry. And you can control the number of the length of the alkyl group, the number you can control. If you do such a chemistry, you can progressively make nanochitin into a hydrophobic material. You look at this. This is a neat nanochitin. Look at the contact angle, 86.5. As you increase the number of alkyl group, you see your progressive increase of contact angle. The highest value go to 158.2. So you can make hydrophobic chitin. Just kind of having a lot of alkyl group. And you might ask, what is the use of this material? This is an excellent additive oil, structuring the oil, controlling the viscosity of oil. If you want to put chitin into oil, you cannot put hydrophilic chitin. You have to make it hydrophobic. These oils are hydrophobic. Let me show you another interesting work we have done with Slovenia. My PhD student went to Slovenia and he did some wonderful work. You can see this paper in carbohydrate polymerase sometime back. We published it. My PhD student Sridhar went to Slovenia and he combined PVDF and nanochitin together. Look at this, PVDF and nanochitin together, and he made an electrosponge system. And he made membrane. And he found that he wanted to remove indigo carmine dye from water. This is again a very important dye being used by textile industry. If you use PVDF alone, the removal efficiency is something like 22%. But if you combine PVDF and nanochitin together, the removal efficiency becomes 88.9. So you can make wonderful filters by combining PVDF and nanocellulose together. Let me now show you some of our work with waste starch. Dear friends, we are not touching the food cycle at all. We collect only the waste material from agricultural land. If you go to the agricultural land during harvesting, you can get a lot of waste. So we collect waste potato, waste rice, waste wheat, waste sorghum, and waste cassava. And we are able to make nanocrystals from starch, a simple acid washing. Thanks to Alain Dufresne from France, he's the father of this bio nanomaterials. Look at this is a slide from Professor Alain Dufresne. You can see beautiful nanocrystals made by him. We followed his path and made nanocrystals. And a PhD student of mine put these nanocrystals of starch into natural rubber latex. And you can see by increasing concentration nanocrystals, we got a very high modulus material. Natural rubber became a high modulus material. And she made a beautiful cartoon. You can see that this is the macromolecules of natural rubber, and nanocrystals of starch made a network. And this network immobilized natural rubber chains. That is why you have an increase in modulus. My last slide is, these are concluding remarks I want to make. See, the waste that we get from agriculture, land, and fish industry, they're all very useful. I'm sure that we can work together. We can transform them into value-added material. Using nanocellulose, you can make fantastic filters for water purification. You can make wound healing material, wound dressing material, sustained platform for antibiotic release, energy storage, EMI shielders, very flexible EMI shielders we can make. And nanochitin is again a wonderful material for water purification. Removal of heavy metals from soil. We are working on that. Additive for oil. And starch is again, nano starch is again a wonderful reinforcing material for polymers. And it's again a good material for packaging applications. I'm posing a question to all of you, to all my good friends. Can we become a zero waste planet? My answer is yes. We have to intelligently transform all this waste into advanced functional materials useful for society. Let's all work together to make use of all this waste into advanced functional materials. And this way we can safeguard our planet for the coming generation. I would like to thank all my co-workers. They did excellent work in my laboratory day and night. Lali, Vaishak, Bibin, Eldo, Dibu, Shirak, quite a lot of people. They're all now in different positions, different parts of the world. I'm thankful to Professor Siena Rao from the chair of Nano Mission. He supported me a lot. Professor Rao is greatly acknowledged. I would like to thank ISRO, CSIR, DBT, ICT, all the funding agencies in the country. International funding, PIX France, India, Sweden, India, Slovenia, TWAS project, DuPont, General Cables, Surface Street, Czech. Indian companies like MRF Tires, Apollo Tires funded us. And my collaborators, Daniel Pasquini from Brazil, my colleague Nanda Kumar from India, Fernando Gomes from Brazil, Alcedes from Brazil, Matthew from Sweden, Eve Hens, Maya Johnson from South Africa, Didier Ruxel from France, Miran Mosetic from Slovenia, Euro Silva from Slovenia. So several people have supported us. I thank all of them. This is my group in chemistry. You can see fantastic, brilliant students. And this is our collaborator from France, Eve Hens. This is me, and you can see our PhD student, Dr. Hannah is here. This is our group in nanoscience and nanotechnology. It's a big group. And this is the present director. When I took over as a vice chancellor, he's looking after the Nano Center. Those who have not visited India, you are most welcome to Kerala. Please come to Kerala and spend some time with us. There's some pictures of Kottayam. It's a God's own country. Kerala is a God's own country, so you have every reason to come to Kerala. We have Kathakali, the traditional art of Kerala, dance of young girls, Mohiniyattam. We have beautiful canals where you can have a boating, the backwaters, waterways, very old temples. This is my campus, so most welcome to my campus. And we are organizing an international conference on macromolecules, September 10, 11, and 12, of course, an online conference, so all are welcome to attend this meeting. I'm also editor of nanostructures and nano objects. Those who work on nano, please submit your article to this journal, is Elsevier, traditional journal, no fee, not open access. The site score now is 6. That's a site score of journal. We are trying to build up a very high impact. So thank you so much for your patient hearing. Thanks a lot. Thank you, Professor Malik.
Okay.
Thank you, my colleagues.
Okay, thank you, Prof. Sabu, for enlightening presentation on nanocellulose. So, from your presentation, I can conclude that nanocellulose is a super versatile materials for various application, and also nanocellulose and polymer has a very low impact on people and also environment. So, in a way, we are preserving our environment, right? So I open a question from the audience if you have any question to ask. Okay, one question coming up, Prof, from Dr. Zahirani. His question, do you aware of carboxylated nanocellulose? The first question.
Yes.
Okay, the second
Yeah.
one, if you do, how does it differs to the conventional nanocellulose?
You see, if you put carboxyl groups on the surface of nanocellulose, this we have done for water purification. If you can put carboxyl group on the surface of nanocellulose, then you have negative charge. So then you can have electrostatic interaction between nanocellulose and other molecules. So this is a very important chemical reaction that you can perform. The nanocellulose and different organic reagents, and you can functionalize them. You can make it electropositive or electronegative. Very interesting question. You have more questions?
Okay, sorry, Prof. I want to ask you a question. Okay, let me repeat my question. I would like to ask you, is everything okay, Prof?
Yes, sorry.
Okay.
Yeah.
Okay, I would like to ask you about nanocellulose as a membrane water filter. What about in terms of the reusability and also
Very,
long-term stability?
very interesting question.
Okay.
Yeah, very interesting question. You see, this filter can be reused several times. You see, after a time, all the filters get clogged with impurities. So you have to we have to dissolve all these pollutants and then reuse these pollutants. This, for example, dye, you can reuse it. That's a strategy we have adopted. Thank
This
you.
is Professor Adewi from Nigeria.
Oh, hello, Adivi. Very nice to see
Yeah,
you.
thank you very much. Well, let me first thank you for the good collaboration that we've just commenced, most especially receiving Dr. Yakubu,
Yes.
who just defended his PhD in Nigeria, having spent some time in your laboratory there
Yes.
in India. I also want to greet Professor Malik in Malaysia. I learned she also visited your lab when Dr. Yakubu was there. So he mentioned a lot about you. Thank you very much for hosting Dr. Yakubu. Straight to my question, indeed a very good presentation. I want to ask, in your talk, you you mentioned about nanochitin, and that got me so interesting because in our group, we've been actually working on a chitosan. I believe we convert chitin to chitosan by just changing the amide group
Yeah.
to a main group.
Yes.
Well, what is so interesting is the ability to functionalize nanochitin into hydrophilic form. I know it's a major challenge. I will be so interested on the process that we are able to go through to make chitin itself hydrophilic. It has been a major challenge for us here. So we need to first pass into making it in chitosan before we now attach so many functionalities before we can make it soluble in water. But directly you can now turn chitin into something that is going to be very soluble in water. It is so interesting to me. I think I'm more interested in that area. And of course, given the various applications that are available, like you have mentioned, very interesting if all this waste, we normally say converting waste to wealth. So it is so interesting, and I think I want you to talk more in that regard. Thank you very much.
Thank you so much, Professor Adi, for the nice comments. So chitin and chitosan is a wonderful material. What we do is my PhD students go to the fish market and collect the fish shell, and then we do a acid treatment. So you can remove all the amorphous part to wash away. And finally, we could get nanochitin. Nanochitin advantage is very high surface to volume ratio. And nanochitin is, it's not very hydrophilic, but you have the water contact angle is around 88, 86. We made it hydrophobic. We made it hydrophobic by putting a lot of alkyl groups. So you can do a lot of chemistry on the surface. You can make it extremely hydrophilic, putting a lot of hydrophilic groups. You can make it extremely hydrophobic. And this is nanochitin because of very high surface to volume ratio. Nanochitin is an exciting material for environmental remediation. You can trap metals, heavy metals using nanochitin. Much better than chitosan and chitin because chitosan and chitin, if you look at the surface to volume ratio, much lower than nanochitin. Therefore, nanochitin has tremendous use because you are in the nano regime. So this could be utilized for water purification, could be utilized for air purification, soil purification. You can trap all the heavy metals. A very good material for additive for oil. So you can use it for a variety of applications. So dear friends, don't throw away all the waste, utilize them in the laboratory. And you can sell them worldwide. That's what we are going to do in the campus. We are setting up plants in the campus. We registered a company for the campus, and we are going to sell all this material for a variety of applications. So we can work together, Professor Adi, jointly.
Okay, thank you, Prof. That's a very good one. Yes.
Thank you, Adi.
Any more question to Professor Sabu Thomas? You can straight away ask to Prof if you have any questions.
Good morning, Prof.
Good morning, Dr. Nardin.
Prof, if you remember me, I was a student that come with Prof Hazlin before this.
Yes.
Yeah, thank you, Prof, for the facilities. I'm good here.
Very good. Yes.
All right, Prof, I just want to ask, to us to get into nanoparticles, we need to go to several type of kind of treatments, such
Yes.
as physical and chemical, right?
Right.
Okay, but in your opinion, which treatment that you will propose to use compare of those two treatment? Is it chemicals better or physicals better?
You see, my suggestion is to get excellent separation, a combination of physical and chemical. That will give you better yield. Combination of physical and chemical together, that is the best. Now we are working with several microbes. Not as successful. All microbes cannot eat away all the lignin and hemicellulose. The best treatment technique is combination of chemical and mechanical. That is very much essential to get nanocellulose. Please use a combination technique.
I see. Thank you, Prof. Have a good day.
Thank you, Dr. Nordin, for your excellent question.
Prof, we have another question. Good afternoon, Prof. I am Alicia, currently doing simulation project on nanoparticle high entropy alloy powder.
Yes, hello, Alicia.
I recognize that you had published books on design and simulation. May I know what is the software that you commonly use in your research? Is it possible to access the book for free? Thank you.
Yeah, you see, I can send you because we always get a copy of this book. One soft copy we store in my computer. Please send me the name of the book as well as the authors. I will check with my colleague and send you this book. And my colleagues use Monte Carlo simulation. We also use all other mathematical tools to do modeling and simulation. So we can definitely work together. I can connect you with my colleague who is very active in simulation, and then we can have a mutual discussion by Skype or by online, and we can do some work together. Very nice comments. And you send me today the details of the book. I will immediately send you for your reference.
Okay, thank you, Prof. Dr. Yakubu, he wanted to ask question.
Hello, Yakubu. Yes, please. Please ask Yakubu. Yakubu, you are muted.
Yeah.
Hello, Prof. Good morning, Nigeria. Am I audible?
Yes.
Good morning, Prof.
Good morning.
Good morning, everyone. My name is Dr. Yakub from Nigeria. I'm a student of Professor Adewuyi, who just talked, and I work under Professor Sabu, sometimes around last year. And thank you for your hospitality. And I want to appreciate Professor Aslin too for her support during my programs. We met in India when I was there, and Dr. Fan.
Yes.
Mrs. Farin, thank you so much. My question is simple. I want to know what is the environmental implication of all these nanofiber? Is there any adverse effects?
Very important question. You see, the environmental impact of this material, that is why whenever you do any work, we also have to do the environmental impact, life cycle analysis. See, my first suggestion is when you use acids, when you use steam explosion, you have to make it eco-friendly. You have to reuse all these aggressive chemicals. Very important, otherwise it will never become eco-friendly. Now we are trying to use more eco-friendly techniques for the extraction of nanocellulose, nanokite, and nanostarch, trying to remove acid. Number one, this is very important. You have to reuse and recycle all the aggressive chemicals you're using. We are also trying to do, microbial, treatment. If microbes can eat away all this amorphous part, that is an excellent technique. And number two, we also have to be very careful about this nanomaterial, where it is biological nanomaterials, biocompatible or non-bio. We have to be very, very careful. If it gets into your water stream, so that can create trouble. Therefore, leaching of nanomaterials even nanocellulose, nanochitin, we have to be extremely careful. That's very, very important. So these are my suggestions to my young friends. Whenever you deal with nanomaterials, please take excellent precautions because they can go everywhere in the body. They can break all the brain barriers. So we have to be very, very careful dealing with nanomaterials. Thank you. Thank you, Jakub, for your excellent question.
Thank you so much.
Yes, thank you.
Yes.
Prof, we have another question from Prof. Haslin.
Yes. Hello, Haslin. How are you? I can
Okay.
see Haslin.
Prof. Haslin just joining us. Okay. Prof. Haslin asks, consistency and sustainability are among the challenges in nanotechnology. Prof, do you think nanocellulose can help in combating COVID-19?
You see, nanocellulose could be an excellent material to make masks and PPE. And you cannot use simply nanocellulose, you have to do some chemical modification, make it electropositive. And that is why our mask design, you see the nanocellulose has been made electropositive. COVID virus as a protein envelope, and then it is electronegative. So you can have electrostatic interaction, and the protein could be made. Sorry, these virus could be made inactive. So I would say nanocellulose has a big role to make masks, to make PP kit, so that the viruses could be killed, protect us from attack of viruses. So that is my answer. We are also trying to manufacture PP kit coated with nanocellulose. Thank you, Haslin, for your nice question. How are you, Haslin?
Fine, Prof.
Very good. Oh, now I can see you, Haslin. Thank you.
All right. Take care, Prof.
Thank you.
So, any more questions from the audience to Professor Sabu Thomas?
I'm sorry to interrupt. I
Okay.
have a question.
Yes.
Okay, you can just go ahead. Okay.
Okay.
Please.
So in the process of gathering the nanoparticle, nanocellulose, there are a lot of source we can take from, such as sugarcane buggers and cattle litter and everything. So my question is, during the synthesization of getting the nanocellulose, is a different source of raw material will give different properties to those nanocellulose, such as the maybe the strength of the material and the percentage of crystallinity and such. Thank you.
Very, very nice question. I have a PhD student. She made nanocellulose from coir, pineapple, banana, and then we looked at the morphology. We found that the morphological structure is greatly influenced by the nature of plants. It's a very interesting question. The diameter, the length of the nanocrystal, and the entanglements, all these are affected by the nature of the plant. So we did some nice work. I think there's a good scope. Look at the nanocrystals and nanocellulose from different plant sources. There could be quite a lot of differences. Yes, in terms of diameter, in terms of its shape, another student of mine made nanocellulose crystal from a very rare plant. We never got needle shape. We got some spherical structures. So it depends quite a lot on the nature of the plant. Very exciting question. Thank you.
Thank you, Prof.
Okay, Dr. Yakubu said we have a lot of waste material in Nigeria. Is it possible to work collaboratively with India and Malaysia?
Definitely we can do that, Yakub. It's a very interesting thing. You see, we have to collect it separately. See, we have now introduced a machine in the campus, and now we are able to separate out cellulose fiber from banana and pineapple. Pineapple, what we get when you have 100 kilos of pineapple leaf, we get only 5 kilo of fiber. the amount of fiber in pineapple leaf is very low, but we are trying to extract it out. And water hyacinth, we get only 100 kilo. Water hyacinth, we get only 1 kilo of the fiber. And then we can make beautiful material. Definitely, we can work together. I think your university also can make a good setup to extract these fibers, and that will give lots of job generation. And you can make fantastic things. You can make fabrics. You can make nano material. So definitely we can work together between India, Malaysia, and Nigeria. Thank you, Yaku.
Thank you, Prof.
Prof, we have question from Dr. Norashikin. From your experience, is there any constraint when it comes for upscaling the nanocellulose?
Yeah, this is a very interesting question. You see, the problem with the nanocellulose is, the demand is very important. You see, now nanocellulose is being used to very sophisticated application. So demand is a very important thing. See, several companies are able to sell nanocellulose. We buy from China, we buy from Sweden, from Canada. But the problem with the nanocellulose is the demand is not that high. I'm sure the coming years, nanocellulose is being utilized for a variety of applications. So the demand will go up. So definitely then the manufacturing will be increased, the cost will go down. And my campus is, we are going to make nanocellulose in the campus, and we are going to sell all over the world. And another manufacturing constraint is, you see, there are different techniques of making nanocellulose. If you use acid hydrolysis, then we must have all the reusage of acid, recycle it. So these are some of the constraints. I think these constraints could be eventually solved, and we are working towards that direction.
Okay. All right. Thank you, Prof. Okay, we have one question from YouTube. Good day, Prof. I am Ono Mei from Southeast University, China.
Very good.
Okay, I want to ask you, what is the level of sustainability of nanocellulose fiber in terms of application in the agricultural sector?
I would say nanocellulose is a very sustainable material because you extract from agro waste. That's my first answer. And it could be utilized for a variety of applications in health, in agriculture, in medicine. In agriculture, what we are trying to do is we are making aerogel and sustained release of fertilizers. This is the area we are going to work in agriculture. You make aerogel, which is porous, and you load this your fertilizer into this nanocellulose aerogel, and sustained release of fertilizer, sustained release of all these medicines we used, pesticides we use for plants, that also could be released sustained manner using nanocellulose platform. This is my answer. So we can work together with the Chinese group.
Okay. Thank you, Prof. Another question. Good afternoon, Prof. Thank you for your nice sharing. My humble request, could you please share with us some tips and advice on how to easily get published in high impact journals and get cited?
You see, one way of publishing in high impact journal is, high impact journal always look at the new chemistry, new invention, new contribution. So if you look at nanocellulose, you can definitely work in high impact journal, introduce new chemistry, a new manufacturing process. So if you can bring in new chemistry, for example, you can see our publication in ACS. We did a small chemistry, and we could publish in ACS industrial engineering and nano applications. And you can also be published EMI shielding material in the ACS. So my humble suggestion is, you jump into novelty. You sort of look in a different angle. And you all have to read high impact journals like ACS, Nano, Nano Letters, Nature, Science. If you read regularly high impact journals, then you get, of course, new ideas. That is the only way. If you can bring in new ideas, new concept, then you can publish in a high impact journal. If your idea, your concept is not new, then you cannot publish. You have to go for low impact journal. That is my message. And the writing style is also very important. The abstract should be quite beautifully molded. Once you read the abstract, the editor should feel that this is something very new. So new concept, new technology, new chemistry will help you to publish in a high impact journal. I would say you have to think out of the box. That's the most important thing. We can support you.
Thank you, Prof. One more question from Dr. Shida from IIUM. She asked, working with natural resources, there are some challenges, specifically in terms of functionalization and mass production. For example, to make it compatible with other materials, we need some other process, which increase the production costs. So to break through the industry is quite challenging. Can you comment on this, Prof?
This is again a very important question. Functionalization of nanomaterial, especially natural material, is a very difficult process. Once you functionalize, it is very difficult to characterize easily, because nanocellulose, if you functionalize, you may not be able to understand well using NMR or FTIR. You have to repeat and repeat, change the conditions, then only you can optimize it. So when you deal with big molecules, characterization of these functionalized surfaces will be difficult. That's a very important thing I want to mention. And regarding the cost effectiveness, this is again a very important challenge. See, once you use lots of chemicals, then the cost will go up. So depending upon the end-use application, you have to prioritize what sort of chemicals you are going to use. That is very, very important. That is why in one of my answers I said, a combination of mechanical and chemical is the best way to make nanocellulose. That's more economical. Therefore, this has to be optimized. Once you optimize it, I'm sure you can scale up this technology. Thank you for your interesting question.
I think we have no question, but maybe one last question from me, Prof.
Yes, thank you.
This is not related maybe to your research, but I just want to ask, because you are on the top position in your university, and you supervise many PhD students, postdoctoral researchers, and then you have many collaboration from industry. So how do you manage this? You manage everything, but you still excel.
I would say these are, I manage these all because of excitement and, of course, commitment and hard work. See, when I publish a paper in a good journal, I'm really excited. When I have a patent, I'm really excited. So science gives you a lot of excitement, and excitement really drives me forward. So I'm really excited, getting up, starting a talk at 8:30 and Indian time, and interacting with you. And, hard work, commitment, excitement, this actually drives me forward. That is my answer. That's where I could get a good number of students with me. They all work hard with me, and collaborators, networking. I also travel a lot. Before pandemic, I used to travel a lot. So I have good academic friends. I organize meetings and symposia every year. Now I organize at least 4 or 5 online meetings. And because of these, I have network all over the world. So you name any country in the world, I have at least 10 to 15 good academics as my good friends. So I request everyone to work extremely hard. You should be inspired by science. And, you should be driven by excitement. That's my suggestion.
Okay, thank you.
You have to be very, very curious, That's very, curiosity is very, very, very important. Yes.
Okay, thank you, Prof, for your beautiful sharing for today. So I'm going to remember a commitment inspired by science, working extremely hard. Excitement in science can drive you forward to explore more in the research field, especially. Okay, so I think I'm just going to wrap up for today. So thank you very much for everyone for attending our session today. So we are looking forward to meet you for our maybe future seminar. And thank you, Prof. Sabu Thomas, for
So
being
much.
with us today. It's such a great pleasure to have you today to deliver your presentation. So thank you, everyone. We'll see you again next future. Assalamualaikum.
Thank you, Prof. Have a good day.
Thank you, Prof. Sabu.
Thank you,
And
Hassan.
thank you very much. Thank you. Thank you. Very well organized webinar.
Thank you, Malik. Thank you.
All right,
Such
Prof. Sabu. Thanks for your sharing. Well organized.
Bye-bye. Bye-bye. Thank you.
Yeah.
Okay, thank you Wani and the committee. Okay,
Okay.
Assalamualaikum.
Okay, thank you, everyone. Assalamualaikum.
Lupa nak request ambil gambar tadi Wani.
Alamak, lu sebenarnya dah letak dalam ni, lupa.
Itulah tak apa.
Tapi ada screenshot kan yang sebelum ni.
Okay.
Okay.
Ada screenshot tadi.
Okay, alright. Thank you semua. Assalamualaikum.
Thank you Wani. Thank you.
Thank you, Wani.
Okay, sama.
Okay.